In this problem, we have a thing sliding without friction down a track. Um, the thing that a lot of students asked me about is the height at this point. This height is just r, because after all, that's the radius of the circle. So, if the block starts from rest at A, what is its speed at B? So, I'm going to do this problem with the idea of potential energy just to change it up. You could also do it with the work energy theorem by thinking about the work done by gravity. So I have kinetic energy at A plus potential energy at A plus work done by other forces, which I don't have, equals kinetic energy at B plus potential energy at B. Work done by other forces is 0. Since there is no friction, the only force here that does work is gravity. Note that the normal force does no work. So putting in these things, we are starting from rest. So that's 0. And I have mg times 4r, because mgh or mgy is the formula for potential energy, equals the kinetic energy at B plus the potential energy at B, which is mgr. So I can cancel all the m's. This will very often happen in problems of this sort. That gives me that VB squared equals, well, we'll do it in 2 steps, equals 3gr. So VB is the square root of 6gr. Now, we're asking what is the force of the track on the block at B? So that normal force has to push the thing inward to keep it going in a circle. So there is a normal force here. And that's just going to be v squared over r. Remember, we are going in a circle. So this part just reminds you that the things you learned before still are true, that this is v squared over r, which is 6gr over r, which is 6g. Excuse me, normal force is mv squared over r. The acceleration is v squared over r, and I have got to multiply by m to get the mass. I knew this was wrong because 6g is an acceleration. 6mg is a normal force. So that's problem 3. That was a pretty simple one.